Okay, let's start our second day afternoon session. So this session we are going to see photophysics and some of the excitonic process in conjugated organic semiconductor. As I said, all those process in optoelectronic devices based on exciton. You might have heard already well known about what is exciton. Exciton is nothing but is a whole electron bound charges. So both when light hit on the semiconductor, then electron will go to the conduction band, then holes and still electron and hole still in the bound charge is not separated, it's still bound level. So that's called your exciton. So after diffusion into the thing, then exciton will dissociate and separate into charges. That's for organic photovoltaic. In OLED, we apply the holes and electron injected into the organic semiconductor. Then holes and electron will meet in the active layer. Then when it's recombined, it will emit energy. It will emit exciton. Okay, that is, it will, the energy is come as a light. Okay, so there are both are is interconversion process. So in this case, I am going to talk about today some of the photophysics in terms of organic solar cell, in how it is useful, how all the photo physics and the excitonic process is happening there. So in this lectures, I'm dealing with this topic, and the outline of this topic is under photophysics. I'm going to talk how the exciton is generating, after generation where it's going to dissociate, and after dissociation how the charge separation is happening, then transport, and how charge extraction, because we need to, after charge separation, we need to extract the output, then only we can use it as a useful current flow actually. So the next one is the charge transport. So how do you define this charge transport inside the organic material? There are different methods to characterize this charge transport. That is one of the things, OFET. OFET I am not doing much in this lecture, because we are going to see organic field effect transistor. OFET is tomorrow, separate. We will discuss in detail. And next things I will do the photo sleeve. Photo sleeve is nothing but is using photon. It's charge extraction using linearly increasing voltage. That's what called sleeve. So third one is space charge limiting current. Yesterday I just to introduce what is space charge, because when we join the PN junction, some of the charge will go to other side, some of the space charge will, how this space charge will affect the charge transport, we are going to, how we use this space charge limiting current to derive the charge transport. So finally, I talk about what is time of flight. See, these all four methods can be used to find the, somewhat is the mobility. I know mobility of the charge carrier is generated in the organic photovoltaics. Okay. Okay. Now this is one slide show that if you want to study anything about what is application, there are a lot of application. This one I already gone through. Because of this material is very easy to manufacturing like this. Even though now studying spin coating, when in initial stage we prepare in different way, at the end of the things, finally everything will come to this printing what we are doing, and the application is like this. Okay. So another thing, if you see the development of this is best research cell published overall in the worldwide. In this chart, it giving all the solar cell people are working in the internationally. So these multi-junction, these are all, left hand side is all are from silicon based one crystal. The right hand side is our thin film technology, where is a perovskite and organic solar cell, everything is there. If you see the top, everything multi-junction cell. We only here have to compare the cell of it is a single crystal silicon cell, non-concentrated. If this is square silicon, where is it coming from? This is coming around silicon heterojunction. The performance is around 26.1. The best silicon cell so far reported is 26.1. If you see this one around, next is perovskite. Perovskite also is close to 26.1. Now the perovskite solar cell reaching close to watt silicon, but still perovskite is not yet in the market, because perovskite solar cell got a lot other drawbacks, because perovskite basically from lead based one, because this efficiency from lead based one. Lead is so toxic, and also still little bit issue about the stability, because this perovskite, if the water droplet is drop on it, it will everything dissolve. So those toxicity issue is still there, that's why it is still not in the market. But that is a good example to develop some other perovskite like lead-free perovskite. What we learned from this perovskite, people are developing non-lead-free perovskite now. Next thing is we are introduced organic solar cell, the red dot you can see. Where is it reaching there? If you see this one red dot, in 2005 it started in only very low, less than 3%, it's going on. Now it's reaching 19.2%, if you see red dot. So already this research in last year 2022, that now the 19.2 went up to 20.4, 20.4 or 5, yeah, the recent board. Anyway, if you see this one, this closely tell that, so we are in the regime of 19.2. So still organic solar cell means, why we are talking about this is less toxic, not comparing to perovskite is non-toxic, and also many of the things is organic material is mostly biodegradable, we can make it, and also we can make it flexible, everything. There are a lot of advantage comparing to perovskite. It's not toxic as compared to what is in perovskite. That's why people are saying. Still, this one also, even though 19.2 is a lab scale device, and when you go to the extent to large scale, still issues. The module will give around at least only 70% of what we are getting in lab scale device. That's the maximum we can get. Still, we need to improve the efficiency as well as stability wise, because when you go for in actual cases, this solar cell is have to work on like at least 80 degree in sunlight. At the time, how stable is organic? That is questionable sometimes. So still those type of challenging is there. Okay. So next, I am saying that how these cells are made. So the very initially people are, as I said, in silicon cell we learn everything from silicon, then organic we learn something new and we are applying. So everything is a bilayer. The first cell is developed in organic solar cell is a bilayer. We make this p-type on top of transparent electrode. We coat CPC is a p-type semiconductor. Perylene tetracarboxylic one is n-type material. Then we go to anode. So this gave efficiency of just 1%, close to 1%. If you see this architecture, the transparent electrode and donor acceptor and metal, this is a device structure. Okay. In this one, the exciton is created here and diffused into the acceptor, the junction, okay, where this exciton, the electron dissociate. At this junction, the exciton dissociate. Once it dissociates, electron will go to the n-type in the acceptor phase. Holes will remain here and travel to the donor phase and get extracted this I2O side. The electron will get extracted through metals right hand side. So like this, the charge can be separated. Okay. So in this one, what we need to consider that, so when the exciton is generated here, it must diffuse to the junction, then only it will get dissociated. So it should have some of the diffusion length, the exciton. This is the intrinsic property of diffusion length. Depends on the material we are using, like basically it's a dielectric constant, then your diffusivity will be very high. So if the exciton diffusion right now the diffusion length of the exciton is very low, less than 15 to 20 nanometer. Okay, that's why we need to have the acceptor in diffusion length of in 20 nanometer. That's why we need to have a dopamine size of in less than 20 to 25 nanometer. Then only exciton can diffuse into the donor acceptor junction. It get dissociated. If it is not reaching the donor acceptor junction, it will recombine and the energy will be wasted because the charge cannot be separated. So exciton cannot be dissociated to get separate the charges. Then it's a waste energy actually. So this is a simple mechanism. We will go in detail. So the next thing is because of this bilayer have this limitation, what we can, if we can make a device with the junction is close to each other, then we can efficiently dissociate the electron. That's why this single heterojunction concept will replace by bulk heterojunction. Bulk means just heterojunction, but many heterojunctions together, that's called bulk. How we can do that? That is called this one. Like I said in the morning, we just mix both, instead of making one layer and another layer N type, we mix both together so that donor and acceptor phase are very close to each other. Then we coat it, then we'll get a lot like this. Comparing to the previous one, here donor acceptor phase are very close nearby. So here one heterojunction, here one another junction, everything the PN junction will form closely within the layer. The many junctions are, that's why it's called bulk heterojunction. So in this case, we can have exciton easily encounter this donor acceptor junction, get easily separated. So again, once it gets separated, the holes will remain into the donor phase, the acceptor, because I am saying that the blue color is acceptor, red color is donor. The holes should be in the donor phase and get extracted from this side. And you can see that there should be a continuous pathway of network to the holes to charge. The holes should travel to your anode, and the electrons should travel to this way to collect it here. So like this bulk heterojunction. Here, not all the separated charges can reach the electrode. There might be a recombination will happen, because when you travel, the holes can be encountered to the acceptor. If it is encountered there, it will recombine and it will go as radiative loss. Okay, so this is a bulk heterojunction concept. Okay, how we, this one I already gone through, how we make this bulk heterojunction. I say that we mix a solution and coat it on the device. Already we have coated with the P-type material and spin coat it, and we anneal it, because when you have the solvent, we need to get rid of all the solvent to anneal and make a film, and complete the device by coating with the electron transport layer and aluminum. This is a device fabrication process. And once the device fabricated, we can see this is donor acceptor phase, and how to characterize, that's another thing. So this is the device JV curve look like. Okay, the JV curve, if you see that this is the short circuit current. Short circuit current means if you close the circuit, what is the maximum current we are getting in that current. When you make it circuit open, when you measure the voltage, this is the voltage we get. Okay, so this is some of the characteristics, voltage and the short circuit current fill factor, and the efficiency is 3.5. EQ is another factor that is tell you that suppose ideally we want to have, if it is a one photon we are giving into the device, we need to get one electron out. If it is the case, we will get 100% efficiently. No device in the world will get to 100% efficiency. There will be a lot of recombination and a lot of loss will be there. That's why silicon also the best efficiency is only 25.6%. Okay, we have only 20, that much only we are getting out. One photon, one electron out means 100%. We only get, if it is one photon, we will get only maximum 0.25% only getting out. Remaining will be recombined, is waste charge. So here we are getting one. This is a very early stage. In 2003 they got 3.5. Just now you saw how is the improvement going on. Is starting from in 2003 3% to now is come up to 20.4% device in last I think it's 20 years time. So this evolution of this development of this organic solar cell. Okay, so what is this? How do you measure? I just a little bit go through about this characteristics. In this characteristics, this is one, because this is one is typical exponent, the diode characteristics. We know that what is diode characteristics is I equal to I0 exponential of EV by KT. It's a standard equation. You can already know that what is a diode. This is an exponential character. So that's a diode character. This is when any diode at dark current, in dark situation without any light, it will give like this. No, but as soon as when you light, we can see the current, short circuit current. So this is the one we make. Ideally, we want have high short circuit current and high VOC. Then we will get efficiency. How do you calculate the efficiency? Efficiency is a power conversion efficiency equal to power output. How much we are getting output with respect to what input. Input is here is a light. Light also we can convert it into power. So in the output we can multiply current with the voltage, nothing but it's a power, right? You know that. So anything you can current into voltage, we already know the power, and input light also power, we can say that is what you can. So here this is short circuit current and this is VOC, and fill factor is not like normally when you get this type of the exponential curve, We ideally want that it should be flat and suddenly it go recombine. Something we need square. Normally we don't get like this. Something like square like this. If it is square like this, the fill factor will be high. Fill factor is how good square will getting. That's the thing. If it is this one highly square, the fill factor will be high. If it is like this, the fill factor will be low. So that means, is it a fact we multiply this one here in this IV curve, the maximum power point, because we multiply current into voltage, you will get the power. So where we can get, these are all multiplication of x and y axis. Where we get the maximum power means somewhere here, the maximum power. That's why you put square is, this point is the, where we can correspond, this is a maximum power and where this. So if you divide this inner square with, we divide this outer square by inner square, the ratio is called fill factor, because the inner square is completely show the squareness. Okay, that's called your fill factor. You can say that the VMPP, this inner square VMPP, JMPP, divide by the outer square, that is JSC and VOC. This is called your fill factor. So this fill factor and short circuit current, JSC and VOC, if you multiply all these things, that's called power output we are getting. And power light input is your sun, one sun. So the P light is, what is one sun means? It's called 1000 watt per meter square. You can say that 1000. I didn't give the number. I said once. I said when I think P light is one sun. We said 1000 watt per meter square is a standard one. All the solar cell is reported that in the measure in the one sun condition. That's 1000 watt. And also condition is sun. The illumination condition is 1.5 AM. The condition. What is incident light 1.5 AM? AM is nothing but air mass. Air mass means, what is air mass? When actually, if in reality, when the sunlight is you have to cross through the air atmosphere to reach our Earth's surface. So when it, when you travel, when the rays are traveled to the atmosphere, some of the illuminations may not be right. Suppose if the light is straight above, intensity is more. If it is in crossway in 45 degree, the intensity is different. Okay, this naturally you know that. So we are not always getting this sunlight in the straight away. We can get from all over direction. So we fix that at 1.5 AM. What is 1.5 AM? When the sunlight is at the zenith angle of 48.2 degree, what the power we are getting, that is around 1.5. How you calculate? The simple action is 1 by cos theta, AM equal to. If you put this 48.2 is in cos theta, 1 by cos theta, 1 by cos 48.2 is, we can calculate this 1.5. If it is straight away 90 degree, 0 degree, if it is cos 0 is 1, then the AM will be 1. If it is AM 1 means the sun is coming straight away. That is AM. The sun is exactly overhead, that 0 degree. Normally we will take sun radiation. What is the sun is coming at 48.2 degree. In that conditions, what is 1000 watts per meter square? It's one condition. I am saying that what is we are not saying, not putting anything just under the light, we will measure the current. No. We need to set up the input light power at particular frequency and what current we are getting, what voltage we are getting. That one we can exactly calculate what is efficiency, because we should not report, if you miss this input light or anything else, anything divide. If the number is very low, the divider is very low, then your PCS will be, your current efficiency we can report is very high. Okay. If it is very high, if the numerator is, if the denominator is very high, this will become very low. So these things should be, we can take care of when you do the characterization, all these measurements of solar cell. I'm just giving that what is the thing. We need to give 1.5 AM and short circuit current and VOC, and this is a factor. And another factor is quantum efficiency. Quantum efficiency means, because we have the solar spectrum of 300 to up to 1000, 1100 we can measure. Not all the wavelength lights are same. As I said previously, the light intensity is varying in different wavelength. Some wavelength it will give the lot of power, the spectral rate is different. So we can also calculate for each wavelength how much electron we are getting, how much power, okay, each wavelength. So that will give the quantum efficiency, will calculate what current we are getting for each wavelength. Then we will find out each wavelength the current, then integrate the whole thing, then we'll get a EQ. Then we'll get a, what is the total current. So each wavelength we get a power, and for each wavelength how much electron is get. Like this, we will calculate everything else and finally integrate whole thing. So in this one, in that same here also we will say number of electron extracted for input of one photon, how much is extracted, that is called EQU. The maximum is 100%. So normally EQU percentage is less than 100% only. Yeah, this is some of the basic things to measure characterizing this organic solar cell. Okay, not any solar cell. Okay, next again go through the in detail about this photophysics process. In this photophysics, I just start with the bilayer. This is a p-type donor material. This is n-type acceptor material. As I said, when the sunlight is fall on this cell, the p-type, I'm only talk about only p side. So there is a possibility the light can absorb even this side also. This also can generate electron. Then this one go through. There is 2 channel also now is going. Previously in earlier case, the organic solar cell is dominantly based on the fullerene based. Fullerene means is PCBM. So PCBM is a very good acceptor, is high mobility, but is a high band gap. The absorption is very less comparing to the donor. So in those cases, the most of the absorption is happening only the p-type material. The fullerene is used to separate the charges, separate the electron. Okay, separate the electron from the exciton. Okay, so here if you in the p-type material, so when the sunlight fall on this heterojunction, first it's upon excitation only the exciton is generated. Is, as I said, is a bound plus and minus charge. Then it will diffuse to the junction. So first state is exciton generation. The exciton generation is the first stage. The second stage, the exciton diffuse to the interface. The interface is maximum, they say 15 nanometer. Maximum it can be not more than 20 nanometer. So the diffusion, the heterojunction the exciton should meet the heterojunction within this 20 nanometer. Suppose if the distance is more than 20 nanometer, it will get recombined and wasted. So the heterojunction should be in the distance of less than 20 nanometer, and it can reach the interface. Once it reaches interface, the exciton, it will get dissociated. After dissociation, the electron will go to this acceptor phase. The holes will stay here and will travel back to the holes. So this is like a charge transfer state. When it reaches the interface and the charge transfer happen. So this charge transfer will also happen at a particular condition. That's why in this case we choose the acceptor, the energy levels. For example, this is a LUMO level of donor, this is a LUMO acceptor. So the LUMO level of acceptor should be somewhat below than the donor material. That should be a significant amount of offset energy should be there to get exciton to dissociate, so that the charge can be separated from donor to acceptor. If you are not maintaining this offset, it won't get separated, because electron will can jump from donor phase to acceptor phase. If there is a difference of LUMO level, because this is higher to lower, easily the electron is transferred to LUMO level. So this is called a charge transfer state. So when you mix these two material, if you are not choosing the material with the enough offset, it won't get separated. You won't see good performance in this one. Okay. So the choice of choosing donor and acceptor also is very important, because as I said, if you want to get a good charge dissociation, we need to have good offset between the donor and acceptor. So this dissociation is very important to get the charge separated. Okay. So next, after the separation, the electron travel to the charge extraction, where the electrode is connected. The electron acceptor is called cathode, and after that the hole is again go back to this one and go to the anode. Then finally it will go as a useful current. Okay, this is the overall process of what's happening in the organic solar cell. Okay, this is, so the inverse of this process is called OLED. We will see the other things in last day, light emitting device, where exciton is generated from light, we are separating out. Opposite way, we inject the charges and we recombine and get the light. Maybe you can easily understand. So if you understand this one, that is very easy. Okay, I think you can easily, because it is exciton, you need to understand exciton means bound holes and electron. That's the meaning. So the main difference between organic solar cell, why silicon is so different is this bound distance is very high in silicon so that it can easily separate out. This is very close. That's why we need to have this much offset to separate out. In silicon is we no need to worry about this one because everything is same. Okay, that's why we need the offset is coming because this charge is so bound. We have to give the energy step difference, energy step difference to separate out. Okay, now this process, how this one, because why we need to have very thin layer means this charge transfer, the charge transfer from what is happening from here to here is ultra fast things. You can't imagine what is things. This happen in femtosecond. You see this measurement, when you have the generate the exciton, it will the charge is travel to the acceptor in 40 femtosecond. You can imagine what is femtosecond. You know what is nanosecond is 10 power minus 9. Picosecond is minus 12, femto is minus 15. You can see that even 1 millionth of nanosecond, that's called femtosecond. So that means very, very ultra fast charge transfer. Okay, that means very fast. That's why we have to make this layer very, very thin. Everything, if it is and also the heterojunction we need to make very close. Otherwise, we have to everything make it in short distance. The donor acceptor phase you should be very close to each other. Okay. And another thing, loss mechanics, because this have basically the VOC is nothing but energy, right? The generation of VOC depends on band gap of your material. Everything is where is coming, your band gap. The band gap what you are choosing, that is the main energy, because that is the energy levels we already seen in the previous class. That's energy level between the HOMO and energy. That energy only is going to use in these devices. So maximum, this is the energy level of HOMO, LUMO and donor, and this is acceptor. So if you make a useful device, you have to maintain this offset so that to get charge separated, so to get dissociated and charge separated. Okay. And in this case, this is the maximum. Any devices, we can't get the open circuit voltage beyond this band gap. Anything less than 1, because there's a limitation. So in this maximum also, we are losing a lot of energy. Energy in the sense I'm talking about is the voltage, the band gap. That's band gap also nothing but energy. Okay, then energy only band gap. Then band gap only light is absorbing, because whatever input light, the energy should be higher than this band gap. Then only the exciton can be it can exit electron. If energy is very low, it won't get. Why the silicon is only absorbing 1100? You know that because that band gap is 1.1. Yesterday I said 1.1. That 1.1 is close to 1100. So only it start absorbing from 1100. Below the things, the energy is very low to excite electron. That's why we can't have any absorption longer wavelength than 1100. 1100 means it's 1100 nanometer I'm talking about. Okay, that's why it's all depends on band gap of this material. Okay, in this band gap we are losing some this energy to charge generation, because if you say that from band gap to charge transfer, we are losing this amount of energy Eg minus ECT for generating charges. After generating charges, the charges should move through the acceptor or donor phase. During the course of travel inside the acceptor phase, it can encounter another acceptor, another electron thing, then it can cause recombine. Okay, when it during, what I am telling is during this, the energy transfer pathway, once it charges, for charge creation itself there is energy loss. During this travel time, because everything is a bulk heterojunction, this electron can be recombined and lost if you encounter another holes. In the donor phase also, when the electron travel to holes, we can't say that this path is free. Still lot of material, accepted donor material is there. It can encounter this another n-type material and it will combine. Only there will be a lot of holes coming out. The holes or electron which avoid all those impurities, then only that only can get extracted out. Remaining most of these get recombined. Even after successful traveling of this electron on this pathway, those things only we can able to collect. So there are something is loss is happening. What is a loss? This much is a loss, because even though the charge transfer state is in this level, we lose this much energy due to during the charge transport. Finally end up we get a VOC of only this level. Okay, even though our band gap is, let's say if you have the 1.8 voltage band gap 1.8 1.7, we will just only real output we are getting only 0.9. That's why most of the cell, if you are doing that, even though donor type is the band gap is 1.8, we'll get only 0.9 or 1 volt is the maximum one. Even silicon solar cell is open circuit voltage is, if we have a band gap of 1.1, we'll get only 0.5 or 0.6 is a silicon cell open circuit voltage. Where is the loss going? Even though we use 1.1, how the loss is happen? The loss is two stage. One is from charge generation loss. The second thing is a charge recombination loss. Charge generation loss is coming from when the exciton dissociate to separate the exciton into donor holes and electron. That's a charge generation loss. After charge generation, the charges should be collected to the, until it travel to the electrode, it loses some of the energy. That's called recombination loss. I hope you understand some of the concept why. Because why we are getting 0.5 when we have the band gap of 1.1. Okay. So in this bulk heterojunction, this is some of the pictorial diagram which says that how it's traveling. I am giving this one. Imagine, because polarized donor acceptor is a, even though I say this one, there should be a continuous network of donor. Okay, it will get, this is cathode, is anode means. Then the block space is somewhat fuller in N type. Okay. When exciton is created, it's travel to and get separate out. But we can't expect that the holes only travel to this way, on the way. It can travel this way, it can travel anywhere. If you can travel in way, this again the holes will encounter here and get recombined. If it's luckily if it travel to this way, then it will get extracted. So we can't expect it where it's moving. And also this most of the energy travel to this way. Why? Because we are maintaining some built-in voltage. I don't know what is the concept built-in voltage, because when you connect this solar cell here, I can say we choose when the anode and cathode. If you see the anode and cathode, we have the cathode is work function of around 5.2. The cathode work function is around 4. Silver, we need silver or aluminum is 4. So we have the difference in work function. So that will create a built-in potential. So when you have this potential is there, that will, the built-in potential will attract, in cathode side, it will attract the holes, because if it is a negative side, it will attract holes. In the anode side, it will attract electron. Okay. Like this built-in potential also will help you to extract the charges. There are multiple pathways there. One is inside is a donor acceptor. The offset is helps to generate the charges. After generate, when you have the charges travel inside the active layer, the external built-in potential will help to extract the charges. After, even though the charges are encountering lot of recombination in between, whatever the charge is moving without encountering all the recombinations, which will move towards, what is the driving force to move to the cathode? Why can't it move to this side? The hole should be expected to go to this one. The cathode, the electron should be expected to go this side. Why it's going means because of the built-in potential we are maintaining with the different work function of this metal in anode and cathode. That also will take effect in this case. Okay. So the same thing, the concept is silicon also with the thing. So the built-in potential you understand it separately. So if you have more electronegative atom, it will attract the holes. If you have electropositive, it will attract the electron in this side. So okay, now another thing I am saying that if it's a donor material, this is all acceptor material. If you see the, I'm going to explain that how the offset is helping in the actual solar cell, because if you are not maintaining any good offset voltage, you will lose the exciton generation. Because I said, if you want to generate charge generation, we need to have a little bit offset level, so that only we can generate charges. Without charge generation, you can't get any current output. The first stage is thin. After that also there is another loss is there. We have to cross up this loss first. So we have to maintain this offset level properly. How this proper offset arrangements will helpful in devices. I'm going to show that. Here I can see that the offset of 3.53 for donor, these are all acceptor material is 1 by 3 point. If you see this one, the offset is only for 0.3 to 0.4 if you see this one. But when you compare this device performance, all those devices, this ITAC and ITs, all those things, we are getting only 3.2, 2.6%. Everything, the fill factor is low because when you have IDTBR, which is somewhat higher, the offset is, when you compare this offset and this offset, the 3 point, this is a somewhat longer gap, more offset energy, and we can see the performance. But still, the potential of this two material, we are expecting that the performance is more than 10%. But because of this material, but if you use some other different material like PCBM, the offset is 4.2. Even we can see that 10.6% here. You see, PCBM is not even absorbing any material because PBM high band gap, whereas this is a low band gap, it will also absorbing. So when you have the high, maintaining the high offset energy, we have a very good short circuit current, and we have VOC, and also you see fill factor. Fill factor means, I said the squareness of this material is improving, and we get that. Even though this material is got a capacity of more than 10% efficiency, because we are not maintaining the enough offset, we are getting the loss of devices. So this will show that why this charge generation, in effect, in other words, we can say how to maintain the offset between the LUMO level of donor and LUMO level of acceptor is very important in charge generation, and how it affecting the device performance you can see from here. You can able to see from here. Okay, so this one, all these three is gone one because it's a lower offset. So another acceptor material, we got same thing. We somewhat decent offset from this one. So this also will give effects of around close to. It's not as good as this one, but we have a decent performance, very high short circuit current, and we got a close to 9.6. Here the performance is low. We got a like 0.56%. This will give some idea about what I talk about photophysics greatly. When you want to generate efficient devices, efficient manipulation of your exciton, we need to have a proper offset of donor and acceptor, and we need to have good mobility of the material so that charge can easily transport to the donor and acceptor phase and to get separated out. Okay, and also another thing is the built-in potential we are creating. The built-in potential we can manipulate with the interface between the donor and the metal what we are using, and the acceptor and cathode layer. So that's called interface engineering, how we can manipulate higher. So those lectures, interface engineering, that will be a last lecture in the Friday. So that one that's only the part how the interface engineering will helpful to this. It's not only one factor to get a good efficiency. I said material is first one, the designing. After that, next one I said making a good, choosing good donor and acceptor with the good energy level offset. And also next thing is good mobility. The other thing is the good selection of your anode and cathode. In between that, interface also very important, because all those things happening in organic, but charge extraction is happening in organic electrode, because all the silver and I2Os are inorganic. When you connect this organic to inorganic, we need to have proper interface. Otherwise, the charge cannot be extracted. So how we can do that? That's a separate class. We'll do that. Right now, you got to understand how the energy can get lost and how we can stop it, how we can reduce it. Not we can stop it, but we can reduce the energy loss. Okay, so far we talk about all these the energy loss and the photophysics. Now we come charge transport. I'm going to here talk about so here the mobility is electron mobility and hole mobility, because if the holes are traveling in the donor, that's called hole mobility. The acceptor is electron mobility, and we have OFET and everything. So the unit for mobility is centimeter square volt per second. This is nothing but mobility is you can define as how fast the electron is moving in the phase under the influence of electric field. Okay, that's your mobility. That's why it's a velocity divided by electric field per second. Okay, this is a simple OFET device, organic field effect transistor. You can see this is I think most of you know how the transistor works, emitter based collector. In field effect transistor, what is given is called a source, drain and gate. It's not a emitter based collector. You can call source gate and source and drain. Actually, the charge transport path is going from source and drain. This charge flow can be controlled by gate voltage. That's a control. Whether we can make it on state or off state depends on your gate voltage. You can imagine this this tap water where we can control the flow of water by adjusting your gate. We are also adjusting the valve. So if it completely stop, if it completely open, it will on. It's the same analogy. We can use it for OFET condition. So by changing your gate voltage, your source drain voltages keep on increasing. And here we can have this type of, this region is called linear region. This is saturation regime. And from that we can calculate what is the mobility. We'll go in detail in tomorrow. We'll go to the next one. This is another one is photosleeve. Photosleeve is nothing but charge extraction by linearly increasing voltage. That's called sleeve. What we are doing here is we have a device like this, anode and cathode. So what we do is in this side, we apply the laser pulse. So when you have the light pulse, it will generate the charges. It charges once just one pulse, then charge generated, it moved to the cathode. That one we collected. That charges we collected by applying linearly increasing voltage, because when the pulse are during the course of time when we apply the pulse here, after the fraction of microsecond we start applying voltage some zero. This voltage we know we can have the voltage is a square potential, linear potential. We can have this triangular pulse. We are applying for triangular pulse because triangular means it's linearly increase if shoot to 3 volt or whatever the maximum voltage it will increase, then suddenly it will stop. Okay. So when you apply this voltage, what will happen? Whatever the current is generated here due to the light pulse, that will be extracted. Okay. So that current depends on how the light pulse is generating the charges. That's what we are getting. If you see this one, the black curve is sending but without any light. The bulge is showing that is the current coming from because of the laser light, the laser pulse. Okay, this laser pulse. So this A term in this equation there is 3D squared is D is thickness of this layer, and 3 by 8 is squared. A is nothing but U maximum voltage divided by time. How much you are applying voltage and how during the what time period. So using this, if you know the thickness and if you know the what time durations, we can find the mobility of this low conducting materials. Okay, this is one of the way, because this is we are applying for linearly increasing voltage. That's why we call it is a current charge is extracted by linearly increasing voltage. The term itself is self-explanatory. You can understand that what is this technique is called, why we call it. Okay, we are extracting the charges by applying, because any charges, no, if you apply external one, we can either you can make it recombined or we can have it extracted. Okay. Okay, next thing is you can say, okay, how this is affecting the devices. When you do measurement, this type of mobility, the mobility also varying according to different material got different material. That's a material property. Not only the material property, we can also study how the film is get arrangement in the film, whether it's a crystalline, whether it's amorphous. So that also affect your mobility. So now we see that sleeve is one of the process to mobility. But when you do the mobility, this is a diaphragm structure. This is dibenzene triazole, this one, and the phenyl DPC. This is a structure I am giving, dibenzyl triazine, and this one have more alkyl chain. This one even 4. So we have a different type of material arrangement. You see, this is somewhat 10 power minus 3 mobility is gave, and this is comparing to this one. This molecule is giving only lower mobility, and even this one is still mobility is very low. Okay, 10 power minus 4 only it's giving. So in this case, the diaphragm material have very good arrangements, got higher mobility comparing to this one. You have to understand one thing here. Anyway, tomorrow we will going to see the OFET. OFET, all the measurements happening in horizontal because the charge is traveling in horizontal. But in all the cases, your device is in vertical. Vertical means your anode is in the bottom, then your active layer and cathode is in the top. So here the travel should charge the vertically. Everything is extracted. But in In the OFET device, it's a horizontal movement. It's not vertically. It's charged from source to drain, it's traveling. So those things, when you have any mobility calculations, the measurements, the mobility, the parameter we are getting, the final value will be different because both are different charge concept. So you can expect that this mobility will be higher than compared to this mobility, because if the thickness is more, still we can get mobility sometimes lesser, but horizontal mobility is always higher. But still it give the good indication of some comparable things. But if you are measuring 2-3 material, which is a good material, like you can good comparison will give. It may not have the good mobility of material. It all depends on what application you are going to use it. Okay. So next thing is I'm giving this. I'm comparing this mobility with the performance. Suppose if this 3 material, if the mobility is low, but the performance also, if you see that this is only highest 3.2%. When you have tips TBC only 2.2, and this is 2.25. When you see that this performance with the mobility one, because why people are comparing the mobility means once the charges get separated, how mobile this one, then only it will reach fast to the external electrode. If the mobility is low, then charge will move very slowly. It may get high chance to get recombined. We may not efficiently extract these charges. Okay. If you have high mobility, it will move fast, it will get easily extracted. So it's quite natural to expect that material with the reasonably good mobility will have a good power conversion efficiency, because we get a good extraction of those charges. Okay. That's why if you have a increasing mobility, you have increasing performance in all the cases. Okay. So again, whether this is the only factor to improve the performance? No, this is not only factor. We can say this also one good performance, but this is the only one. This is one of the one, I can say that. Okay. So in this one, this is a linear sleeve process. Sleeve process we can do different way, because when you apply the linearly applying voltage, we can improve the voltage. We can apply 1 volt. We can apply very small. So we can apply the 3 high. If you apply the higher voltage, we can extract more current. If you want a less voltage, because normally if you apply high voltage, we can expect the high current like this. How much linearly? If you apply 3 volt, we get a high current. If you get and 2 voltage, the current is very get less. And also it depends on. It's quite expectable that according to what voltage you apply, we can get extract more current out of it. But again, this current, this varying current doesn't affect your the carrier extraction time. So that's why I said the carrier extraction is not time dependent. Everything is extracted at the same time. Even irrespective of what voltage you apply, the maximum current is always fall on the same thing. You can see that. And also the mobility only is varying according to the thickness of the field effect actually. So everything linear variations. Here another thing is time delay. What is the time delay means? So when you apply the laser pulse, where you are start applying the voltage, because when you apply the voltage linearly, the linearly increasing voltage, that time only you can extract the charges. Suppose we apply the pulse here. When you apply the pulse, the charges, photo charges will get generated. You have to immediately start measuring. But if you hear that time delay is more time, that time the generated charges will get relaxed. It will be recombined in the active layer itself. Because if you apply the voltage very late, we got to apply the charges immediately so that the charges get extracted. Because if you not that, the charges can easily recombine and we can't able to extract. That's why if you increase at that time of time delay, if you have more time between the laser pulse, the charge generation and the charge extraction, if you have more, we can't able to extract the charges. That's why if the charges delay is increasing, means almost we are not losing very less charges. When you have the very less time delay, we get more charges is important. This is also a very good indication that we can extract the mobility of how mobile your charges are. Suppose if you are extracting charges even at a different time delay, means your generated charges have high mobility. Something you can say that. Okay. So this one graph will give that with the time delay, how much mobility you are getting like this. So next thing is I am saying that here we are comparing this mobility with the two different systems. One is TIPS dibenzene triazine, and other things P3ST PCBM. In the P3ST PCBM, the mobility is always high at 10 power minus 3. Here in this system 10 power minus 4. That's why we get lower lower performance because low mobility. It's not only for low mobility, and also we need to have a balanced. What do you mean by balanced mobility? In the organic solar cell, we're using donor and acceptor. If the donor, after the charge separation, the donor and acceptor, you are expected to be same mobility line. Suppose one is higher mobility, the other one is lower mobility, means your holes will be, if for example your donor is higher mobility, after charge separation your donor will go fast. But to get this electron out, we need to have equally electrons should come out. Otherwise, you can't extract the charges efficiently. So you need to have a balanced mobility. Your whole mobility allows electron mobility almost equal, so that you can both charges equally come extracted than current. If one charges come, if electron is not come, then charge cannot be extracted, if not that. That's why here if you see that in that case, the whole mobility 10 power minus 5, the electron mobility 10 power minus 3, there is a mismatch is there. So that causes also the device performance to go down. For the case of in P3ST, almost I didn't give the P3ST, the electron mobility, whole mobility is almost equal. That's why we are getting the somewhat good, decent performance. Again, the performance 3.2, the absorption is something different. Only the high band gap, low one. But the fill factor, we can tell that that will give the, if you have the good fill factor, if you have the balanced mobility, you will get the high fill factor, then good device performance. So it's not only mobility of one charges, the mobility of both phases should be equivalently good for making the good performance. And this one, another case, another thing is how we can extract. So far, I'm talking about how the charge transport is happening, how the good mobility. Okay, when this charge moves, what is the recombination effect? I said if the hole is electron is moving on the acceptor phase, there should be a hole will come. When the electron meet the holes, it will recombine. We can extract. So what is the recombination? So that is the one factor is called Langevin type diffusion control recombination. That also we can calculate by using. For in this case, recombination, this bilayer recombination, the Langevin 165 minus 8 per centimeter square, and for this is for P3ST, and this is for the recombination is very low in the case of dibenzene tyrosine and comparing to P3ST. Even though this is having very unbalanced charge transport, but the lower recombination is still low, but this is somewhat contradictory result. But the recombination is getting, ideally we want to have low recombination, because so those things, this may have that answer, maybe they may have the higher phase separated domains, or we have the charge carrier gradient will be there. That's one of the reasons why we are getting this lower recombination. Even though we get a low recombination, but the performance is still low. There are other factors dominant for the lower performance of this DBC based OPV device. Okay. So next I am going to talk about this space charge limiting one. So space charge limiting current is, as I said, so we are in this current. Space charge means, as I said right now, if any charge conduction, we have electron and holes we can extract simultaneously. If you are injecting one charge just going on, if you don't have enough electron, the charge will be only settled in one side. Then the space charge will be developed there. So that will cause further movement of other electron. In the space charge, what we are doing is, we are maintaining only hole only device, because if both side, this is also p-type, and aluminum also, gold also high work function, and p dot also high work function. Normally if you want to have a device, this will be high and this will be low work function. That's why efficient. Here we purposefully make it both are in high work function. That's why the device can allow the conductivity of only one charges, hole only. The electron cannot be injected. Here in one side you can inject only holes only. This side we can electron inject because this work function is very high. So this device we make in such a way that we only inject only the holes, so that the hole will be stagnant, create a space charge inverse. From that we will deduce what is the mobility of this one. So how we can do mobility? This is the formula to derive the mobility of here. The J equal to 9 by 8 mobility term, and dielectric constant V squared by d cube. How we arrive this equation? Basically is start from current equal to sigma E. Sigma conductivity is electric field. Again, sigma is charge density NU and mobility of Y. This is a very basic conduction mechanism of charge coming from Ohm's law. Actually, we can come J equal to sigma V. So from this one we apply that because if you see this one as when you have two electrode and middle is a dielectric, it's nothing but simple like a capacitor one. If we act as a capacitor, because two electrode middle is any insulator is called capacitor. We can call this is nothing but an insulator. Then we can call capacity is equal to epsilon A by D. Then you have again the electric field. So I'm saying that this the charge density Ne equal to Q is the total number of charge and A is volume. A times T is a volume. Again Q is nothing but CV by AD. Then you will get epsilon E by AD squared. Again if you submitted C equal to from epsilon A by D, finally we get epsilon B VD square. So if you apply this NE to this application and E is voltage divided by time, then finally we get into this formula equations, because we consider basically start from this one, so and finally end up with this license by using this one, by using this current and voltage curve. This is a space or limited current. Then we deduce what is the charge carrier limit. So in this method we use this three type of material. We calculate the mobility of these three things, because this is a very low performance material, but it have a very low mobility of -8, -7 and -5 only. Okay, what I am showing that this is another way to extract these charges to find the mobility of charge carriers. This one method. There is another method I want to tell you that is time of flight. Time of flight also somewhat similar to what we studied in sleeve process. Sleeve process we apply the external voltage. Here we are not applying. Without applying external voltage, we are measuring the current. That's the time of flight. So time of flight, what is saying that this is a device. We apply the pulse here. The pulse will generate the charge without the influence of any external voltage. They are trying to collect the charges here. Okay. For example, if the pulse is applied here, so when the charges move and when you get extracted, we will get a charge. When you apply the pulse, the charge will get extracted. Once all the charge is extracted, then it will come to 0. So here what we do that we will measure where the charges get completely extracted. That is at this point. We calculated this is the transit time. After the transit time, the charges become 0 because all the charges get extracted. From this unit we derived from the experiment by substituting this one into this d squared by Vt. We know that what is d is thickness of your device d. By knowing what voltage pulse we are applying, then we can find this transit time, then we can easily derive what is the mobility of these things. Again, this time of flight experiment is the mobility value is coming from this equation, famous one. From this one the mobility is coming from d squared by Vt squared. You know that electric field is nothing but is voltage divided by time, V by D, and velocity is nothing but distance by time. By substituting this factor, finally we can arrive this one. So in this device, we make normally this device will need a thick layer of your active layer, then so that whatever the charges generated, it can reach there and it can collect it. So by finding this transient time, substituting, we can find the mobility. This is another way to find the mobility of this one. So as I said, charge transport, finding mobility is very important in device fabrication. These are all. There are some other method. Is this is the most commonly used one. There are some other people talk about dark injection and some absorption spectroscopy, electro-absorption. There is some other techniques. That's not quite popular, but these 3-4 things are you can see in many papers, and these are reliable method to find out. Now SCLC is the most reliable method, and time of flight as well, to measure charge transfer. Why is it very important? This is very important to find out the mobility, because if you know the mobility, generally we can reduce the somewhat recombinations happening in the devices. Okay. So another I'm giving the example of this one. This is a rubrine. How using the equation, how we can calculate the mobility of this rubrine. So here, as I said, when the things are when charge pulses applied, the voltage is generated. After that, it will get 0 dB. So we need to measure this transient voltage somewhat around this thing point. So here in this one we measured the transient time of around 0.71 microsecond, and we apply this 145 in this equation. So simply we can get this mobility is 0.37 centimeter square. This is rubrine crystal, because rubrine is a very good material like this. We can slowly, with the solution process, we can create a single crystal out of this one. Similarly, we can also find the mobility of tetrazine as well using this method. The tetrazine in this one, the same thing there, that the experimental results given here. This is a transit time. The microsecond is given, corresponding mobility is 1.3 second, centimeter squared, everything. So this is a good method. In earlier, people use a lot of time to derive the mobility of organic materials. Okay. So with this one, I will complete this session, and tomorrow we are going to see how is field effect sentence. Why I am giving the field effect sentence separately. So this is having lot of applications. The transistor, obviously transistor applications. We'll see in detail about what material is giving a good field effect, transistor effect, and what is the development in this field, and detail how this is we can fabricate it, and how this one works, and also working principle as well. Second, today I just show that only one slide. I will go in detail and tomorrow first lesson. Okay, you can ask now. You can ask me if you have any questions. Ideally 0.5, remember. Yeah, 0.5. At least that's, even though if it is less than some 0.3, so that is not good. But yeah, it's more than 0.5. That's why we have energy losses. Can you repeat the question? No, everything Dr. said laser pulse, that's we applying the laser, because the charge is generated from the absorption of photon, laser power photon. If you say the time of flight, yeah, photon, not like this sunlight. We have the separate single wavelength laser. SLC, no, not SLC. It's for sleeve and time of flight, everything. Not SLC or OFET. That we are injecting charges in the charges. Yeah. Yeah, it's whatever the injecting charges also is electron and holes, right? That's what we're injecting. Even though from exciton also we are also generating the same holes and electrons. That's why we are mimicking that. We build up the space charts intensely. We create it and find out the mobility, because the theory is like this. We build up the space chart. From this space chart's behavior, we find out the mobility. Yes, because in HCC, that's why the term is come V squared by D cube. If the D cube is the denominator, if D cube is more, this will affect the mobility. Yeah. This should be almost equal, this TOF and SCLC, but as I said, OFET mobility and this one will be different, because both transports are different, horizontal and vertical transport. SCLC, yes, but according to our OLED and photovoltaic devices, it's for only, but only for OFET application. OFET means a transistor. Transistor is nothing but switching devices. So for those one is good, but that's not good for OFET, because both configuration is entirely different. Yeah, both should be equally charged because once you, yeah, yes, correct, definitely. That's why I said the design criteria is a mobility also one of the criteria. Mobility should be fine. Someone is asking? Yeah. No, no, PDOT is not here. Yeah. PRDP. So this have active, though that's whole mobility is only, we can also use blend, we can also use a separate material, the active layer, but the main criteria is the electrode that both should be the high work function material. Not silver, gold. I2 and P dot, yeah, mostly this one. Or if you want to avoid gold, you can use moly oxide and silver, molybdenum oxide, that's a P-type material. Any questions for? Yeah. Sorry. Yeah. Yeah. Contact. No, no, that is different. The external contact is different. Yeah, we are excited. That's important. That one we need to have at least a low work function for electron extraction, high work function for a hole. Yeah, yeah, yeah. That one we can fix there. We know that what is the work function of metal. Already known that. So that one we'll fix. Yeah, that is known. Only the new material is here is organic. That one we don't know what is it. Then one we got to know. Yeah, right. Right. Yeah. For that we need to change the device structure. We have to have low. We, no, we can't use the same thing. For electron transfer, we use silver on top. At the bottom electrode, we can use zinc oxide or titanium oxide like this N-type layer you can use. Yeah, 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 yeah. Low, both should be lower function. That's zinc. People use normally zinc oxide or N-type acceptor, or top layer should be silver only. Silver is lower function comparing to gold. Yeah. That's a differentiating by making the device itself different. That's why devices we can only inject in electron only device we can only inject electron, cannot hole. Not in hole only device we can only inject holes. Yeah. Yeah. Any more questions? Yeah. Now we have exceeding 10 minutes. It's okay. After having a small break, if there is no question, we have a hands-on experience on how to find out the band gap of the material, and we collect the data and do the process, and we at least I brought some P3ST material. We can start with the P3ST. Yesterday we saw how the spectrum. Are we getting the same thing? We can compare. Okay, we do the both solution as well as the fill. Okay, okay, we'll see you soon after your break. Okay, thank you.